Question 4. Now we're considering two functions p of x and q of x. P of x is the natural function natural log x, ln x. Q of x is ln 3x. And the first thing we're asked to do is to show that their derivatives are equal. Derivative of p dashed x is 1 on x, a very straightforward result straight off of our formula sheet, or notes sheet perhaps. And q dashed x, using the formulation f dashed x on f of x, will be 3 on 3x, which equals 1 on x. And that's our show. It is looking good. Okay, next up, we're asked to describe the relationship between the graphs of p of x and q of x. Now, if you look at the function above, it appears that q of x is a vertical translation of p of x, and in fact that is the case. And the main reason why that is the case is this. Using our log laws, we can see that ln 3x is in fact some constant added to ln x, the constant being ln 3, so that gives us our vertical translation by ln 3 units. Okay, now we've got another function r of x, also a logarithmic function. This one is the logarithm of some quadratic expression, and now we're looking at the relationship between r of x and p of x. And first of all, we're asked to consider r of x in the form a ln x plus b. Doing that's easiest if you spot the fact that this quadratic is in fact a perfect square. R of x is equal to ln of that quadratic factored, so that would be ln of x plus 3 all squared. Using our log laws, the exponent 2 becomes the coefficient 2, so it's 2 ln x plus 3. So there are our values of a and b. Now, how does that help us? Well, based on our understanding of transformations, we know that the coefficient 2 is going to equate to a vertical dilation by a factor of 2, and the value b equals positive 3 corresponds to a horizontal translation by negative 3 units, or 3 units left. And so that will be our answer to C part 2. Time for some statistics. This question asks us to look at a discrete random variable x that takes values 1 to 5, being the 5-star ratings on a hotel rating system. And first of all, we need to show that a equals 0.553. The best way to do a show is to actually perform the calculations that lead to that result without sort of pre-guessing what it is. So we start with the idea that the sum of probabilities is 1, and then we can calculate the sum of what we have, do some subtraction, and derive the result we require. So that's going to look a bit like this. So to complete this, I think I'm going to sum the probabilities that I already have. So back to run matrix, and let's start with the summing. So there's my sum of the current probabilities that are given, and so a will be 1 minus that. And I don't need to do too much mental arithmetic to see that a is equal to 0.553. But again, probably best to make sure in case I've written something wrong and I need to explain my error. So that looks good. Okay, now we're going to calculate the mean given to the hotel by its guests. Now, the formula for the mean is the sum of the weighted outcomes, that is, they're weighted by their probabilities, so it's actually quite similar to the data I've already entered. And for that reason, I'm going to grab that line I've put in up here, and I'm going to clip it and pop it down below. So then I do that by pressing Shift and 8 when the line is selected, and pressing F1, copy line, and then come down here, and shift and paste is 9, and that pops the line in. And now I'm going to edit that by adding in the probabilities multiplied by their values. So the 0.045 would be times by 1, no need to add anything there. 0.015 is times by 2. Then the 0.105 is multiplied by 3. This probability there, back there, is multiplied by 4. And then we need to add in the A value, which was 0.553 multiplied by 5. And that should give us the mean value, which is exactly 4.283. Okay, so now we've got the mean. Next up, we're going to show the probability that a randomly chosen guest will rate a score less than 3. A score less than 3 obviously would be a score of 1 or 2. So that means we sum those two probabilities to get an answer of 0.06. Again, because this is a show question, it's important that we show at least some preliminary lines of calculation. Probably line 2 in that example would have done the trick. Right, so now we have a new variable, y, which represents the number of guests who rate the hotel at less than 3 stars, and this can be modelled by a binomial distribution, we are told, particularly when we know how many guests are chosen. In this case, 20 guests are going to be chosen. So that's an important statistic. That will be n in our binomial distribution. P we've just calculated as 0.06. So we have ourselves a distribution for y, which is binomial with n equals 20 and p equals 0.06. Now we want to calculate the probability that exactly 2 out of 20 guests will rate the hotel as having less than 3 stars, and I'm going to use the statistics mode of my calculator and the binomial section of that to do that. So back to menu, off to statistics by pressing 2, the distribution menu, binomial. I'm going to choose the point distribution. We're interested in 2 out of 20. With a probability of 0.06, and pressing execute, that gives us a value of 0.225 to 3 significant figures. So that's calculation number 1, part D. Calculation number 2 is more than 5 guests. Given that this is a discrete random variable, more than 5 means 6, 7, 8, etc. So it starts at 6. And this probability can be calculated not in the binomial point distribution, but in the binomial cumulative distribution. To get that, exit a couple of times to get the distribution option up again, and then back in we go. Distribution, binomial, cumulative distribution. The values in here are already set n and p wise, but our lower bound will be 6 and our upper bound will be 20. And a very small probability, 0.000869. Okay, now to part E. Part E is now about interviewing past guests and taking a random sample to make sure that at least someone in that random sample gave you less than 3 stars so you could interview them. So now the question is, what sample size would be required such that the probability that y was greater than or equal to 1 is greater than 0.9. So now we're working with binomial distribution that has an unknown size n. Now there are 2 ways to go here, and I'll show both of them. One way to go is if you're feeling confident with the binomial distribution formula and you recognize that the probability of greater than or equals to 1 is 1 take the probability of x equals 0, the only thing that's not greater than or equal to 1, then we can go down this path. First of all, realizing this. And because that's a single value of the binomial distribution, we can use its formula. That would be Cn0, 0.06 to the 0, 0.94 to the power of n being less than 0.1. Those first two terms are 1, so we have 0.94n to the power of n is less than 0.1. We can take the logs of both sides and then divide by ln 0.94. It's important when you do that to realize that this inequality will switch around because the log of 0.94 is negative, and that's because the log of anything less than 1 is negative. So the inequality switches around, and ln 0.1 over ln 0.94 is what we want to calculate. That's going to be a job for the calculator, so a quick pop into the run matrix menu, and ln 0.1 over ln 0.94 gives us a value of 37.2. And as n is a discrete value, a number in a sample, we're going to round that up to the smallest value greater than that is 38. Now, for some of us, that method might not immediately appear as an obvious way to go, and clearly another way to go would be nice. The one that I'm going to use here is a bit of trial and error using the binomial cumulative distribution. So this is an alternative. You obviously wouldn't do both of these methods, but the other one would be to evaluate this probability for a few different values. So back to the statistics mode, back to the binomial distribution, the binomial cumulative distribution, and now we are going to calculate the probability greater than 1. If you change from 20 to, well, let's start with 20 and see what it is. So that's a 71%, a long way short of our 90%. I'm going to record my values in a table as the evidence of my thinking. It's going to be important to get those 3 marks that I have some working out here. I'm going to run answers to two figures. So trial and error says we have to increase this value to increase our chance of getting at least one person that we're looking for. I'm going to go to 30 next. You can see that that value is too small, and so we're going to continue to trial and error, recording as we go. Okay, so we've now exceeded our value. We don't need 40 because that's a probability of 92%. So we're obviously in the high 30s here. And now it's a question of whether you go down or up. I'm going to go down to 37. And that value is very close to 90%, but not quite 90%. So I'm actually going to write that one to 3 significant figures, 0.899, and I'm pretty confident that the next one I'm going to get, which will be 38, is going to be right on the money. So let's just double check that. So we can conclude that the smallest sample size you need is 38 because 37 is not quite enough and 38 is just enough. So I think either of those 2 methods will definitely get us the marks for this question. Question 6, and we're getting to the end of book 1, so that's going to be nice. I'm looking forward to turning the page, maybe having a quick cup of tea and then getting back to it, or maybe in this case a cup of coffee, it would appear. So this question is about the concentration of caffeine in blood plasma after consuming a 150 milligram dose of caffeine. I guess that's the delicious serve we're seeing in the picture there, and that function is some form of exponential function. We have a set of axes, and we're going to start off by drawing a graph of that function. So that obviously calls for our first visit to graph mode. Let's go there now, and the first thing is to enter the C function as y1. I should be able to put it in just as it appears. Arrow across to get out of that exponent position. Close that off with my brackets. and that looks like the function entered. But just make sure you can eyeball it. If you want to go back and arrow back up, you can see that full function is looking correct there. Now, before I get silly and press draw, I'm going to make sure my view window is looking precisely as required. I have an axis and I want the axis to match what I'm going to draw. So shift and the view window, and the X scale looks like it goes from around about 0 to 24. So 0 to, let's say 25. And the marks are in 5, so I'm going to make my scale 5s. And arrow down a little bit. The Y minimum 0, and the Y maximum looks like it's 4, and scales of 1 there will match the axes provided. So with that done, I'm going to press execute and then press draw, and I'll see the graph drawn pretty much on the axes that I would require. Now, to make this look good, one key feature that helps you draw the graph correctly is this maximum value here. So I'm going to use my Gsolve menu to find that coordinate and plot it to make sure that my graph is sort of scaled correctly. So Gsolve, and the max command spits out a value at 2.3, and it's as high as 3.75. So 2.3, 3.75, that would be around about there. I don't have to be exactly right, but that looks pretty accurate to me. And we can see that the graph has some asymptotic behavior here. You can definitely see that it's below 1 by the time it gets to 10. So I need to make sure that my graph comes down. Now, if I had a pencil, I'd be using a pencil, and then I would be using pen to finalize my graph. I'm going to have a crack with my stylus. So let's see how I go. Must make sure it starts at the origin. That's clearly a critical feature of this function. Up we go to the maximum, and then we turn around quite quickly, and then we show that asymptotic behavior here, and we probably want to take it all the way, even though it's hard to draw. We're going to show it all the way, heading towards that graph. If you're not happy with that, make sure you might want to come back and do a little bit of shading to show that that's actually a maximum value, and then show that point there. So make the point clear as the maximum point, and then if you're not happy with this, again, make sure that your finished result has the behavior that you're looking for. The key idea here is that we show the behavior of the function. It's not an art class, but it is a important representation that we want to show. Okay, so that's looks like a good enough graph for part A. Let's have a look at part B. Part B says, using the model above, find the concentration after 10 hours. Well, I've got my graph here, and what I want is that value there, but I'm not going to guess. I mean, I can see it's here, but I'm not going to guess. I'm going to use trace. So press Shift and F1, and I can just type in the value 10, and it will jump to 10. And I can see the Y coordinate there is 0.7096, so that would be 0.710 to 3 significant figures. As we're working in context, it's probably worth including the units there. The question wasn't a number, it was how much, what was the concentration. It's 0.710 milligrams per litre, or mgl-1, which is the units we were given in the question. Okay, on to part C. Part C asks for C-2, or the derivative of the function at 2. This trace command is going to be useful once again, so I'm going to go Shift and trace again. Whoopsie, that's exited trace, back into trace. I could have just pressed 2, obviously, while I was there, and hop, I go. We're nearly at the maximum. I can see my derivative values on the screen there. So my value is 0.241. And the units for that is milligrams per litre per hour, because it's a rate. I hope the physics people can forgive me for my unit representation there. Now the interpretation. And the key here is that we're interpreting this not as a gradient of a tangent or some other valid statement, but we're interpreting it in the context of the problem, so we need to make sure we talk about caffeine. So I'm going to say that the concentration of caffeine is increasing at 0.241 milligrams per litre per hour at the time t equals 2 hours, or at the time, or 2 hours after consumption. Perhaps keeping with the context, I'll focus on the consumption. Okay, so that's a very contextual interpretation, but that's what was called for there. Okay, now we've got some calculus. We're asked to show that the derivative is the function given, and obviously, it's a show, so we need to make sure we're quite clear with our working that's going to lead us to that result. So this is a chance to use just some straightforward differentiation power law type job. In this case, it's going to be 15 multiplied by the derivative of e to the f of x, so that's e to the f of x times f dash, which will be 0.3, or negative 0.3, and then the next term was negative, and this one is e to the negative 0.6t multiplied by negative 0.6, and we can see that if we multiply 15 through by that, 15 times 0.03, and you might want to check this, because if we've made an error here, we want to pick it up in our derivative. So 15 by minus 0.3, that looks like negative 4.5, which was the first coefficient we had, and the second one is going to be positive, and 15 times 0.6 will be twice as much as 15 times 0.3, so that's going to be positive 9 e to the negative 0.6t. So result shown. Now obviously that's a useful result, because our next question says, hence, by letting c dash of t equals 0, show the concentration is reaching its maximum at this exact value, t equals 10 on 3 ln 2. So this is clearly a case for not using a calculator, which would definitely give us a decimal approximation for this, but we're going to do this by setting c dash t equals to 0. So let's start with the expression equals to 0. Now I'm going to solve this equation. There's a few ways, but one way is to bring one of those terms to the right hand side. I'm going to move the 4.5 e to the negative 0.3t term to the right, and then I'm going to divide everything by 4.5. That leads us to 2 e to the negative 0.6t equals e to the negative 0.3t. Now is a chance for some judicious use of logarithms. I'm going to take a log of both sides, and I'm going to use the log law on the left, the log of AB being the log of A plus the log of B. So I'll get ln 2 plus ln e to the negative 0.6t equals ln e to the negative 0.3t. Obviously, more logarithm laws required here. Those two terms, ln 2 is going to stay as it is, but the natural log of e to the a is a, so that first term is just minus 0.6t, and the term on the right hand side is minus 0.3t for the same reason. Ln e to the a equals a. And now I'm pretty close. I've just got to bring that t terms, unite them, so I'm going to bring one to the other side and do a quick switch around, so I'll get 0.3t equals ln 2, and that means obviously 0.3 is 3/10. If you invert and multiply, you get 10/3 ln 2, which is the exact value we were looking for. So that's looking good. Now we leap on to part E. Part E is a generalization of the question to date, where now we've got a general function in terms of d, where d is a dose. The dose previously was 150. Now the dose term is represented by this d over 10 component. Now we're told that the maximum concentration for this general model still occurs at the exact value that we've previously found, but what we're asked to do is to show that a dose of 600 milligrams is the maximum amount, and that's going to relate to this claim here, which is that we don't want to have a value greater than that, or otherwise we experience serious side effects. So we don't want to experience a maximum or a peak of our function of greater than 15. So if you think about that graph, we want this peak to be below 15. I'm interested in how that's going to occur. So now we're going to take our exact value, 10 on 3 ln 2, and find the d value for which that is less than 15, and that will be done by substituting it into this generalized c underscore dt function. Okay, so there's an equation that we can start working with, or an inequality we can start working with. So simplification of those exponents is my first port of call. So multiplying the decimals by the fractions, 3/10 times 10/3, that's 1. And that negative is better expressed as an exponent of the 2. So using log laws, I'm going to write that as ln 2 to the minus 1. That's that minus at the front becoming the exponent. And similarly, for the next term, this one, minus 0.6 times 10/3 is going to give me twice as much, so minus 2. And so that will be e to the ln 2 to the minus 2. And that will all be less than 15, or equal to 15 for our safe dose. So now we've got d on 10 equals to the log, or e to the log a, so that's going to be a, so 2 to the minus 1 is a half, and 2 to the minus 2 is a quarter. And if you weren't so sure about that, your calculator would verify all this for you, of course. Dunk, dunk, and then we pop in our exponent. And we, to be honest, we probably could have put in the whole thing. So there's our half or 0.5 value. But given that this is an exact operation, I thought I would try and do this without too much calculator work. But we're now at a point where the numbers are looking quite nice. We end up with, well, a half take a quarter is equal to a quarter. So we get d on 10 times a quarter. So that will be d on 40 is less than or equals to 15. And then by multiplying, we get d is less than or equal to 600, being 40 times 15. And that's our maximum dose. So if we want to stay below 15 milligrams, we have a maximum dose of 600. Okay, so that is actually the end of book 1. So I'm going to move on now with that caffeine hit. I'm going to get started on book 2.